Hi guys, welcome to the post-contest discussion of the Meta Hacker Cup Round 1 by TLE Eliminators. This is Abhinav and I guess we can get started with discussing the problems from the round 1 of the Hacker Cup. Uh, I hope the contest went nice for you all and may all of you qualify for round 2. Okay, but anyways, if you want to solve, let's discuss the problems. We'll just start with the first problem, even snake skills. Okay, so it is given that a solid snake needs to inspect n platforms numbered 1 to n. The ith platform is a horizontal segment from point I A1 to I plus 1 AI. So I AI to I plus 1 AI inclusive. Okay, and Solid Snake starts on platform 1. He can travel between two platforms with a ladder of height h or greater if there exists a vertical line segment of length h that intersect both platforms. So basically, you need to find the length of the shortest ladder that Solid Snake needs to visit each platform at least once, starting from platform 1. Okay, so basically these are the platforms that are given to you. So here you are given that in the form of an array. So if the array given to you was 2 comma 4, so this is the example for the first test case, 2 4 5 1 4. So 2 4 5 1 4, that means that in between, that would just mean in between 1 and 2 there's a platform at height 2. In between 2 and 3 there's a platform at height 4. In between 3 and 4 there's a platform at height 5. Same way, height 1 and height 4. So these are basically the platforms given to you. Okay, now once these platforms are given to you, so the snake would start from the first platform and he wants to travel from first platform to the next, to the next, to the next, to the next. So he wants to travel to all the platforms. In order to travel them, he can use a ladder of height h. So let's say he's using a ladder of height h. Then if the difference between the heights, okay, so if you can, what the problem states is, if you can draw a vertical line of height some x which is less than h, less than or equal to x, so the basically the difference between the heights of the platform, if that difference is less than h, the height of the ladder, then you can travel from the first platform to the next platform. Same way, if the difference between the heights of the next two platforms is less than or equal to h, then again you can travel to the next platform. Then if the difference is less than equal to h, you can travel to the next platform, to the next platform again. So you need to pick a ladder of height h. So you need to pick a ladder of height h and you need to minimize this h. So the minimum height of the ladder that you would pick, so that you can travel to all the platforms. Okay, so you need to just find out the minimum height of the ladder you need to pick to travel all the platforms. So I hope you would have guessed the solution to this. So basically, to travel from the first platform to the next platform, you can calculate what is the minimum height needed. Basically the absolute difference between 2 and 4, the positions of the platforms, the absolute difference between their heights is basically the minimum height of the ladder needed to travel from this to this. Again, from this to this would give you some minimum requirement of height. This to this would give you some minimum requirement. This to this would give you some minimum requirement. Among all those minimum requirements, whatever is the maximum, if you pick that particular height of ladder, then all those minimum requirements would be satisfied. Okay, so if you have like n minus 1 requirements, so between every I and I plus 1 there would be one requirement. Okay, so for all the n minus 1 requirements, all the requirements states that the height h should be greater than equal to some value, some value, some value. So what minimum h you can pick to satisfy all those conditions is the maximum among those values. Okay, so basically you can say that your final answer is, so basically you can say that if you are given an array A, something like 2 4, in the first test case it was given to you 2 4 5 1. So 2 4 5 1 and 4. So if this is given to you, so basically the in between the first and the second platform, the difference between the heights is 4 minus 2, the absolute difference 2. In between the next two platforms, the difference between the height is 4 minus 5, which is 1. Next two platforms, difference is 5 minus 1, which is 4. Next, the difference is 4 minus 1, which is 3. Among all these difference, you need to pick a height which is greater than all of them. So the maximum among them is 4. So you would pick a ladder of height 4 in order to satisfy all the conditions. So basically you can say your answer is just the absolute difference between AI and AI plus 1 for, so the maximum among the absolute difference between AI and AI plus 1 for every I from 0 to, you can say, n minus 2. Okay, if you are taking zero based indexing. So for n minus 2 and n minus 1 would be the last difference that you would compare. So this is basically your answer for this. So the given constraints were still very less, n 100, AI 100. So calculating the maximum would take you an order of n time only. So order of n is well accepted for this problem. Let's look at the code for the first problem. So we take the input in the array A, and then my final answer is mx equal to 0. I iterate from I equal to 0 till less than n minus 1. Maximize the absolute difference between AI plus 1 minus AI. Okay, the absolute value of AI plus 1 minus AI, just maximize that in the variable mx would be your final answer. Okay, so I hope this first problem is pretty clear to you all. So I guess we can move to the next problem, the harder version of this snake problem only. Okay, so in this harder version, the initial statement remains the same. Additionally, solid snake may travel between any platform and the ground if his ladder is long enough. So the ground can be modeled as a segment from 0 to n plus 1 to 0. So basically you can say that you had these platforms from 1 to 2, all these platforms were there. Now you can just consider this ground as another platform. Okay, so just from n0 to n plus 1, you can just consider this ground as another platform given to you. Now once you consider this, and now the snake starts from the ground, he would start. In the previous problem he was starting from the first platform, but now in this problem the snake is starting from the ground. Now starting from the ground, now you need to check. Now you can travel from the ground to some platform also, ground to some platform also, using a ladder, or one platform to another platform also using a ladder. You can choose whatever you wish, and in that way you need to find, like, can you travel through all the platforms. So here in this example case, what you can say that here to here in this platform using a ladder of at least size 2. From 2 to 4, again a ladder of at least size 2. From 4 to 5, a ladder of at least size 1. After that, here, instead of traveling from 5 to 1, which would take a ladder of size 4, what he did is, instead of that, he came back to ground, and from ground he traveled to this platform. So the size required was just 1. From 0 to 1, only a ladder of height at least 1 is required here. So from ground again he traveled to this, and from this he traveled to the next platform with a height of 4 minus 1 3. So like among 2 2 1 3, 3 was the maximum. So you can say that with a ladder of size 3, with a ladder of height 3 only, you can just travel to all the platforms starting from ground. But if ground was not given to you in this same test case, you were needing a uh, you were uh, you were required to have a ladder of height 4. But with ground given, you can just travel to these, and then from come back to ground, and from ground again travel to them. Using a ladder of just height 3 only, you can travel to all of them. So the minimum height here was 3. Okay, so now you can understand the problem is kind of changed. You cannot apply the same logic you were using in A1. And here the constraints are given as 5 into 10 to the power 5. So that means you cannot do something like n square and all. You have to do something like order of n, or at max n log n would also be fine with these constraints. Okay, So now how do we solve the problem? Okay, let's try to think. So now what you are given is uh, now you are given some platforms like this, and your ground is also a platform. So ground is also a platform. You can consider the ground also as a platform. Now with this given, how do you traverse through? So starting from ground, how do you travel to all the platforms with minimum height? So first thing is you want to minimize your height. Okay, so if let's say you if you can travel to all the platforms with a ladder of height h, can you say you can travel to all the platforms with a ladder of height h plus 1 as well, h plus 2 as well, or anything greater than equal to h? If you can travel to all platforms with a ladder of height h, then for anything greater than equal to h also you can travel to all the platforms. So you can guess that this would be like a predicate function that initially for some small value of h, let's say h equal to 0, 1, 2, maybe you are not able to travel to all the platforms, but maybe with a height of 3 you are able to travel. If you are able to travel with a height of 3, then for 4, 5, 6, for all of them you would be able to travel. So it would be something like a 0, 0, 0, 1, 1, 1 predicate function. So you can apply binary search to this like for any kind of maximization problem, binary search on answer is kind of intuitive, should come to your mind directly. So once you know you can apply binary search on this, now the problem only remains is inside the binary search, how do you write the check function? What would be your check function now? Check function would be just check of, you would check the mid value in your binary search. Check of mid would be 1 if you can traverse through all platforms using a ladder of height h is equal to mid. Okay, so if you use a ladder of height h, okay, check h is basically if you use a ladder of height h, can you travel to all the platforms? If you can compute this check in even in order of n, then overall n in n log n you can solve the problem. So just focus on trying to find the solution for this check function. Now you want, now your lad the height of your ladder is fixed. Okay, your height of the ladder is fixed. Okay, in check mid, or you, let's say check h only. In check h, that using a ladder of height h, can you travel to all the platforms? Now your height of the ladder is fixed. Okay, so if height of the ladder is fixed, now you know that whether from ground to this platform can you go or not, from this platform to this platform can you go or not, from this to this can you go or not. Okay, it would be just a boolean value like yes or no, are they connected or no. So if, when would I say that you can travel to all the platforms? If starting from ground all the platforms are connected, so you would always start from ground. So first of all, from ground you would have to reach some platform. Okay, so let's say high h is such so that you are able to reach this platform, but you are not able to reach this platform, this and this. Okay, so let's say this was a little bit higher. Okay, so let's say you are able to reach these two platforms from the ground itself, but all the rest of the platforms, their height is a bit more than h, you cannot reach them. So basically, first of all, you will try that from ground where can we reach. Now from here, rest of the platform has to be reached from those platforms which you reach through ground. So from here you can reach here, here, or here to there, or from here you can go in the left side also, this way, this way, this way. So for any platform, in order to reach this platform, there is just two ways, or you can say three ways to reach a platform. Either you would reach from the platform just to the left of it, or you would reach from the platform just to the right of it, or you would reach here from the ground. There are only three ways to reach any platform. So from the ground, you can just initially calculate whether you can reach a platform from ground or not. And then for the remaining rest of the platforms, they are just two ways: either reach from the left side or reach from the right side. So what you can do is just iterate two times, once from left to right and once from right to left. So let's say you are iterating from left to right. So this is the platform you have reached. So if you have reached a platform, try to connect it to the next platform to the right. If yes, then go on, keep connecting, keep connecting. Once you say that here, let's say we after this, here let's say we cannot connect, this height was something greater than h, so you would stop there. You would say, yeah, this got connected, this got connected, then this cannot be connected, so you would leave it cross. After that, move ahead, like if this is cross, you cannot travel to next if you haven't traveled to this, so this is invalid, you don't need to check here, here. Then you travel to this platform from the ground. Okay, if there is some platform to the right of it, check to the right. Okay, so once you have covered traveling from left to right, then do one iteration traveling from right to left. So from here, let's say you try to travel there. So if this height is sufficient, then you can travel here and mark it a tick. If this height is sufficient, mark it a tick. This is sufficient, mark it a tick. If at some point you say that this height is not sufficient, it is greater than h, then let it be a cross. And again, here, if you have already traveled and you can travel to the platform to the right, which is across, then mark it a tick. So once you have done one iteration from left to right and one iteration from right to left, after that, if there is still some platform left which is unvisited, then you would say that you cannot visit all the platforms. Because if you can visit this platform, then there were only three ways: either from the ground, which was not which we initially only checked, or from the left. So if you have done an iteration from left to right, then if it was possible to travel from the left, you would have gotten here, and or from the right. So if you have done an iteration from right to left, if it was possible, you would have gotten here. Now you would argue that maybe from right to left you traveled this platform, and then from left to right you travel some platform. But if you are saying that you travel a platform from left to right, and then from right to left you will travel back to the same platform, so if it was possible to reach from here, that means this was already visited. Then going from here to here doesn't make sense. So at so in this way we can say that for any point, in order to reach here, either you would just reach from a sequence of right 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 only, or a sequence of left 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 only. It would never happen that you would reach a platform by going right right then left then right, some zigzag way. This would not be optimal, because if you are going from right then left, that means this is already visited, then going back right doesn't make sense. Okay, so you could have visited it from just by going right from there only, instead of going left and then going right. Okay, so this way we can say that if you do just one iteration from left to right, one iteration from right to left, you would cover all the platforms that you can cover. If still some platform is left uncovered, then you return 0 for your check function. Okay, and once you have written this check function, you apply the binary search to find the minimum height, minimize in the binary search to find the minimum h which satisfy the condition. Okay, so this way we can solve the problem in overall n log of ai. You can say the range of your low and high, the range of h would be the values of ai, which is till 1 in 9. Okay, so let's look at the code for this problem. So what we can say is we take the input array, and then for the range of our answer, either a height of 0 would be enough. So if you have like only one platform at height 0, something like that, or all the platforms are at height 0, then a ladder of height 0 would also be sufficient. This is the minimum, and maximum is 1 in 9, because if you take a ladder of 1 in 9, then all the heights are less than equal to 1 in 9. So from ground only you can reach all the points. Okay, so 1 in 9 is the maximum you would take. So this is the range of my answer, and I take an answer variable. I apply the binary search while low is less than equal to high, mid equal to this. Okay, now for this particular mid, I'll check if it is possible to travel to all the platforms with a ladder of height equal to mid. So I create a visited vector. So initially all the platforms are unvisited. Now I start once I'll start from left to right. From 0 to n, I am moving. If this AI is less than equal to mid, if the height of the platform AI, so AI is basically the height from ground. So if this height from ground is only less than equal to h, then yes, we can travel to it. If height from ground is less than equal to h, we can travel to it from the ground only. So once you'll check if you can travel from the ground only, it's fine. You mark it visited, move ahead. Otherwise, if you cannot travel it from the ground, then the other way to travel this is you are moving from left to right. So you travel from I, if this I minus 1 platform is already visited, then you can use this difference to travel to this platform. So we'll check if I is greater than 0. Obviously, there exists a platform to its left, and that platform to its left is already visited. If it is not visited, then you cannot visit it from that. If you have visited that I minus 1th platform, then only you can come to the ith platform. So if it is already visited, then take the and the absolute value of AI and AI minus 1 is less than mid, then you would mark it visited. Okay, these are the two ways this platform can be visited while moving left to right. Same way while moving from right to left, if the platform just to the right is visited and their absolute difference is less than mid, mark it visited. So once you have iterated left to right, then right to left, if still in the visited array there is something, the count of 0 is not 0. So if the count of 0 becomes 0, that means all the platforms are visited. That means the answer to my check function is a yes. So if the count of zeros is 0, that means you have visited all the platforms. Then answer equal to mid, high equal to mid minus 1. Try to minimize the answer more. Otherwise, low equal to mid plus 1. Increase your mid so that you can visit all the platforms. Okay. So after applying the binary search, we get our answer. Okay, so I hope this problem is pretty clear to you. The time complexity would be for applying the binary search, it is log of 1e9, and inside that you are using two loops of order of n. So this is order of n and this is order of n. This count function would also take some order of n time to count. So again, order of n only overall. Inside it's order of n. So overall we can say this is n into log of AI. Okay, log of 29. So overall, I can say my time complexity is order of n into log of a of I. Okay, so this I can say is my time complexity, and my space complexity would be something. I'm just using an vector of an array of size n and nothing else. So space complexity is order of n. Okay, so I hope this first problem, this second part of the first problem is also clear to you. Let's move to problem B1. Okay, so in problem B1, what you are given is Meta employees love two things: building cool products and scaling them up as a new intern. Okay, initially your empty product has coolness 1. Each of the next 2n days, you'll make a change, multiplying your product's coolness by any positive integer of your choice, subject to the following requirements. That so you start with a coolness value of 1, and every day you would multiply that by some value of your choice, so that it satisfies the requirement that after n days the coolness is at most a. So after the nth day the coolness value should not exceed a, and after 2n days the product should have a coolness of exactly b. So after b days you should have a coolness value of exactly b. So basically just find any sequence of 2n changes you can make to get a final product of coolness value b. The constraints are just 100. So for this, like what you are given is, let's say, let's take the first test case. You can, so you are given three things: n, a, and b. So this is your n, this is your a, this is your b. So you just need to find n is 2. That means 2n is 4. So you just need to find like four numbers, so that so you start with 1, that means multiplying with 1 doesn't change the answer. So on the first day you would multiply 1 by some value, next day multiply by some value, next day multiply by some value, next day multiply by some value. So after 4 days, so basically the product of these four numbers that you choose, the product of these four numbers should be equal to b. Okay. And the other constraint is for the first n numbers, the product of the first n numbers, their product should be less than equal to a. Okay. So overall product should be equal to b, and for the first n numbers the product should be less than equal to a. You need to find such a number. So for this test case you need to find four numbers so that their overall product is 63, and for the first two numbers the product is less than equal to 5. So what four numbers would you pick? So for this you can like, it can have multiple answers, you just need to print any one of the answers. So one way to do that is at halfway point you need to keep the product like minimal, it should be less than equal to 8. So what you can do is just keep them 1 1 1 only. One is the minimum you can keep till halfway point, keep them 1, and after that also you just need to make the product to be equal to b. So you can keep all of them 1 and add this b at the last point. So this construction would always work. So for any given n, a and b, what you can do is pick 1 1 1 and at the end pick a b. So an array of, pick an array of size 2n with all ones, and at last you pick a b. So in this way, in the halfway mark your product would always be 1, which would be less than equal to a. Whatever a is given to you, it doesn't matter. And for the complete product you would have the complete product equal to b. So it satisfies both my conditions. So this would always be a valid construction for this problem. So that's it. For this problem, we'll just print this. Take the input n, a and b. Just create a vector of size 2n with all ones and say that the last value is equal to b. So in this way, you create a vector with all ones and the last value equal to b. Just print that vector. That's your final answer. So that's it. For b1, this was only the code. This construction always works because you needed to just print any one valid sequence. Okay, now let's move to problem B2. So in B2 what we are given is, please calculate how many sequences of 2n changes exist that yield the final product of coulomb. So now in this B2 version you don't need to just find any one way, you need to count the number of ways in which we can do this. Okay. So the number of ways in which we can have 2n numbers, so that they all number of ways in which we can have 2n numbers, so that the product of these numbers is equal to b and the product of first n numbers is less than equal to a. Satisfying these two conditions, how many such sequence of 2n integers exist? You need to count them. Okay. Now, also, if you look at the constraints, here the constraints are very big. A and B are till 10 to the power 14, N is up till 10 to the power 16. So, with this big constraints, like you cannot apply something like order of A, order of B kind of thing as well. You need to think of some optimal solution. Okay. So now let's try to think what we need to construct. So for any valid way, what you need to construct is you need to have 2n integers. Okay. You need to have 2n integers so that these 2n integers product up to b. So first of all, what can you have at every place? So whatever things you have at any place, they all would be a factor of b. This thing like you can clearly understand. So let's say you have b is equal to 12. So basically, in how many ways you can get a product 12? Let's say n is 2. So n is 2, that means you need to find 4 numbers which product up to 12. So maybe you can say 2 into 2 into 3, this products up to 12 and take a 1. This is one way of picking 4 numbers that product up to 12. Or maybe you can have 1 1 1 12, which way we are having earlier. Or maybe you can have 1 1 and 4 into 3. 4 into 3 would also give a product of 12, and these positions can well be shuffled as well. Maybe you can also have something like 1 1 and 6 into 2. That would also be valid, and all these positions can be shuffled. So there would be multiple ways to get a 12, but in all the ways these values would be some factors of 12, and you can say you have to basically distribute this 12 is basically 2 to the power 2 into 3. If you do the prime factorization of this 12, if you do the prime factorization of this 12, then this 12 is 2 to the power 2 into 3. Basically you need to distribute all these prime factors at different positions among the 2n positions, so that you get the different combinations. So this thing in itself satisfies our first condition, that the product should be B. Along with that, we also need to keep in mind the second condition, that till the halfway mark for the first n numbers, the product should be less than equal to it. So how do we keeping that in mind, how do we count the number of ways? So first thing is, in order to deal with this restriction of A, what you can do is, now whatever distribution you do of the 2n numbers, it would be something like, for the first n numbers, the product of the first n numbers would be something, and let's say the product of the first n numbers is some x, and let's say the product of the next n numbers is some y. So you would say that product of all these 2n numbers is b, that means x into y is equal to b. Okay, so the product of first n numbers and the next n numbers, if I'm telling they are x and y, then the product of x and y is b. So basically, and the other condition you should have is, this x should be less than equal to a. This is the other condition that should be satisfied. So you need to pick how many first partition you can do is, how many different x and y exist which satisfies these two conditions. So what all x and y would exist which satisfies these two conditions is, basically we need to break b into two factors, so that the first factor is less than equal to some value a. So how many different ways in which we can break b into a product of two numbers? So this you can do, like, how do you factorize a number? So you can do the if you know the algorithm for factorization, you can do factorization in square root b complexity only. In order of square root b complexity, you can do the, you can find all the factors of b. So with a constraint on b was given as 1e14, so square root b would be 1e7. So you can apply this to get all the factors. So this distribution you can do, first thing is there. Now let's say we have distributed them. So what we can do is, while you are finding the factors, how do you find the factors? So if you have a 12, if you have a 12, you would start with I equal to 1, so you get 1 into 12. Then you go to I equal to 2, you get 2 into 6. Then you get 3 into 4. Then once you go up till square root of 12, so once you have exceeded, you won't go further. And then the other factor from here would be 12 cross 1, other from here would be 6 cross 2, other factor from here would be 4 cross 3. So in this way, we got all the factors. Okay, so these are all the factors. So we have got all the ways to distribute this 12 into two numbers. So for all these, we can one by one check. If we keep this as our x and this as our y, is it valid? This as x, this as y, is it valid? So among all these ways, for all which satisfies that the first number is less than equal to a, that way is valid. So that distribution is valid. And how many factors would exist? So the number of factors of some n, the upper bound on the number of, if you know, the number of factors of n is approximately order of cube root of n. If you don't know, then this is like a basic thing that you use sometimes, that the upper limit on the number of factors of a number is approximately the cube root of n. So with b given as 1e14, cube root of b would be something of order of less than 1e5 only. We can take the upper bound as 1e5. So there would be at max 1e5 different distributions of x and y for which you would have to check. Okay, so now once we have fixed our x and y, so let's say we have fixed our x and y, that we need to distribute this b. Let's say b was 12, we need to distribute this b into 3 cross 4 only. So in the first n numbers, you would have the product of first n numbers as 3 and the product of the next n numbers as 4. Now inside that, we need to find the number of ways in which we can have product of n numbers equal to 3 and number of ways in which we can have product of n numbers equal to 4. If you can count that, those the number of ways to do this and number of ways to do that, the product of them would give you the overall number of ways for this particular distribution. Add all the number of ways for all the distributions, all these distributions that you found, which were valid, which were satisfying x less than equal to a. For all of them, if you can find the number of ways to do this and add all of them up, your job is done. So then the next problem is how to find them. So both the problems are in a way same, that you have a number x, distribute x into n integers so that the product of these n integers is equal to x. Okay, so how do you distribute that? First of all, do the prime factorization of x. So let's say if you had some x is equal to 36, prime factorization of 36 would be uh, for power of 2 you have 2 to the power 2 and 3 to the power 2, something like that. So its prime factorization would be of some form p1 to the power k1, p2 to the power k2, p3 to the power k3, something like that. So for this particular case, what we can say that all the there are two 2's present in the prime factorization. So you have to distribute these two 2's in these n numbers. So you can place the first, let's say you can place the first 2 here and the next 2 here. This is one way. Okay, or maybe you can place both of the 2's together and make it a 4 at one place only. So there would be different number of ways to distribute these two 2's in the n numbers. So what is the number of ways for this distribution? So for any p1 to the power k1, basically there are k1 occurrences of this prime p1. You need to distribute these k1 occurrences into n different terms. So what you can say is, for like you can even combine that one place may have more than one occurrence of this one. So you have n places. Let's say for the first place you distribute a1 number of 2's at first place. This a1 may be 0 as well. At the second place you distribute a2 number of the p1 here. Here you distribute a3. So like for 2 maybe for if you are distributing it 2 to here this value of a1 would be, you have 0 number of 2's here, you have 1 number of 2 here, you have 0 numbers of 2's here, this a4 and a5. So you have 0 2's here and 1 2 here. So this would be this array A. So basically we can say that we have to distribute these two 2's into n different places, where one place may have more than one occurrence also. So we, if you take the frequency of how many times we have 2 here, and so those frequencies, the sum of these frequencies should be equal to 2. So the number of ways to have an array of size n that sum up to k, this is what you need to find. So you can use the method of stars and bars and say that if you have a1 plus a2 plus ar is equal to n, so number of ways to have such an array that sum up to n such that ai is greater than equal to 0, this number of ways is defined to be n plus r minus 1 c r minus 1, or which is same as n plus r minus 1 cn. So if you know about this, using the method of star and stars and bars, we can say that this is the number of ways for the distribution. So replicating that here, what is the value of my r and n here? So here then this was this. So basically you have to distribute into n. So the n here is r in this. So in this formula, we would place r is equal to n, and our n here we want to make it equal to what? We want to make it equal to k1. Okay. So n is k, let's say. So basically from this formula, we can say that our formula is uh, sorry. So basically we can say that our formula here is, this was n plus r minus 1, replace n with r and replace n with k and r with n, you get k plus n minus 1 c k. Okay. So this is the number of ways, or you can say n plus k minus 1, n plus k minus 1 ck. So n plus k minus 1 ck is the number of ways to distribute these k p1s into n places. Okay. So now if you can compute this NCR value, then you can say for this first prime, the number of ways to distribute them was n plus k1 minus 1 ck1. For this next one, number of ways was n plus k2 minus 1 ck2. For this one, it was n plus k3 minus 1 ck3. And the overall number of ways would be the product of all of them. So the product of all of them would give me the number of ways to distribute this particular x into n different numbers that product up to x. Okay. So if you can find the prime factorization of x quickly, then these powers, this k1, k2, k3, their powers would be something of order of log of x only. So log of b something. At max it would go like 50, 60. At max 50, 60. This sum of k1, k2, k3. So all these NCR values, NCK, can be found in order of k. So all these NCR values, this overall, in order to calculate all the NCRs and multiply, would be some overall order of 50 or order of 60, you can say. Order of log b only. Okay. Because order of k1 plus k2 plus k3, the sum of the powers would be at max. The sum of the powers would be at max log of b only. So if you can find the prime factorization, then after finding the prime factorization, calculating these NCRs would be something of order of log of b only. Okay. How do you find the prime factorization quickly? That is the next problem. How to find the prime factorization of x? Now this x can go up till 1e14. So you cannot apply a sieve till 1e14 in order to get the prime factorization log n. So if you can apply a sieve till 1e14, then after calculating the SPF, you can do it in log n. But here you cannot apply a sieve. What you can do is, you for b, now since you know this x would always be a factor of b. Okay. So if you can do the prime factorization of b, if you can do the prime factorization of b, so can you do the prime factorization on b? Another way to do prime factorization is in order of root of b, you can find the prime factorization of any number. So this would be 1e7 only, you can apply. So you can find the prime factorization of b, and in the prime factorization of b, all those primes, you can store all the prime numbers in a set. So for x, only those primes would be present in the prime factorization of x. So what you can do is, you can store that primes, you can store the list of primes that occurred in the prime factorization of b, and from this list only you would check for doing the prime factorization of x. So in order to do the prime factorization of x, what you would do is iterate through this list of primes which was present in the prime factorization of b. So iterate through this list of primes and calculate the power for every prime. So the number of primes here would be at max again log of b only in prime factorization, and just iterating through all of them and calculating their powers would be at max log of x log of b time only. Okay, let's say in log of b time only you can do the prime factorization. Just keep dividing for the first prime, keep dividing by that prime until x is divisible by it, that is the power on that prime. For the next prime, keep dividing until it is divisible, that's the power on the next prime. So if you know the primes that are occurring in its prime factorization, just iterating through them, and there are just log b different such primes, just iterating through them, you can find a prime factorization for x. So you can do the prime factorization in log b time. So overall your time complexity for the algorithm is, first you did the prime factorization of b, which took you root of b time, which is 1e, which took you root of b time, which was 1e7. Then you calculated all the factors of b, the all the factors of b in order to get the different x and y, different distributions, all these different distributions. So for doing this factorization, it again took a time complexity of root b time, again root b, which is 1e7. And then for every factor of b, for every factor of b, you get some x comma y, and then you just calculate, you just count the number of ways, count the number of ways, and count the number of ways for x and number of ways for y to distribute them into n numbers. And this counting would require you to do a prime factorization, which would be done in log b time. Okay. And also once you have done the prime factorization, then calculating the ncr, the product of ncr, again that would take a log b time. So in this count function is going to give you the count in log b time. So 2 times log b, and this is done for every factor of b, and number of factors of b which exist is cube root of b, which is approximately 5. So overall this is cube root of b, this is log of b. So overall this whole algorithm takes, this whole algorithm takes cube root of b into log b time. So this would be something like 1e5 into log b would be something like 60. So 6e7 and all only. So overall 1e7, 1e7, 6e7. Overall the time complexity is still less than 1e8 only. So it would run fine. There are 140 test cases, but in general there would be only a few test cases which would give you a worst case complexity of 1e8 kind of thing. In most of the cases you would be able to find the factorization and all in lesser time. So overall you don't need to multiply by that 140. In general you can keep this mind in big hacker cup, like you have to only find output for one test file, and in that it would not happen that out of 140 like there are 100 test cases which are giving you, all of which are giving you a worst case time complexity of 1e8. So that would not happen in general. Even if there are 10 test cases, then 1e9 would still be fine. But actually if you look for the algorithm, in like 1 second only the whole code ran and I got the output. So it was way faster than this only. This complexity which I am computing is like the very high upper bound. So this whole algorithm would be fine to work. Okay, so I hope you got the algorithm. Like we'll look at the code. If you didn't understand, we'll understand it from there. Okay, so first what we do is, inside the function I take the input n, a and b. Okay, now this I'm pre-computing, like just to, although it would not matter much, but just to remove this log b complexity, still if you are feeling that it is taking too much time, then what we were doing to compute the ncr. So always I was computing n plus k minus 1 ck, and this k would at max go up till 60 log b time only. So what I'm doing is, for every k from 0 to 60, for every k from 0 to 60, I have just pre-computed this value because my n is fixed in the test case. So this computing one value is order of 60, computing for 60 values is order of 60 cross 60. So in this much time I can just compute all the values of this n plus k minus 1 ck. For every k from 0 to 60, I have just pre-computed it and stored it. So in combination 60, I have pre-computed all the NCR n plus I minus 1 Ci. Okay, and this NCR I'm computing here in order of R time, going to every multiplying n minus I and I plus. I hope you know how to compute NCR. So I've computed NCR in order of R time. So this overall is taking something like 16 to 60 time. In this must have, I have just pre-computed all these values. So when I need to multiply these, values, I can do them in order of one time only because I have pre-computed them. Okay, so only the factorization would take the log n time. Okay, so this is one thing. Okay, then so to start with the algorithm, first what I'm doing is prime factorization of b. So in the algorithm, first thing that I'm doing is prime factorization of b. So with prime factorization of b, my only aim is to get the primes, the list of the primes that are occurring in the prime factorization of b. So I've just stored a set of int in which I'll just insert all the primes that are occurring in the prime factorization of b. So I start with I equal to 0 till I into I is less than equal to b, while b modulo I is 0. In the set I insert I and b divided by equal to I. So in this way I do the prime, and if at last since I'm only iterating till I into I less than b, so at last I may be left out with some b which is greater than 1, then I'll insert that because that would be a prime number only. If it is not a prime number, I would have got it here. Okay, so if you know the algorithm for prime factorization, that's how we do it in square root b time. So in the p, I have got the set of all the primes. Now once I have got all the set of prime numbers in once I have got all the set of prime numbers, next I'll compute my actual count. So first I'll factorize this b to get all these different combinations. Okay, so like if it was 12, I'll get all the different combinations of the factors of b. So I start with, okay, let's leave these functions. I'll tell you the functions. So I'll start with I equal to 1 till I into I is less than equal to b if b modulo I is 0. So then I is one of the factor of b. So I and b by y. This is one factorization of b. So I'll just count with I as my x and b by I as my y, the number of different combinations that I get. And if I is not equal to b by I, then b by I comma I would also be a different combination, that also I'll count. Okay, so I have to just count. Now what I've written in the count function is, first thing, if x is greater than a, then I return 0. There are no ways to do that. Okay, x should be less than equal to a, then only I'll count. Okay, so if x is greater than a, I'll just return 0. Otherwise I'll write it as func of x into func of y modulo m. So then my count is number of ways to distribute x into n different numbers having product x, number of ways to distribute y into n different numbers having product y. So this number of ways I'm calculating through a function func. Okay, so whatever is the func of x into func of y, that would be the total number of ways for this distribution. Now how do I write my func? So func of x is basically I have to distribute this x into n different numbers. So first I'll do the prime factorization of x. So I'll iterate through all the primes, and while x modulo I is 0, I do x divided by equal to I, and in C++ I'll compute the power of p. So this is basically my k. So in my prime factorization, since for any prime factorization of x, I would have p1 to the power k1, p2 to the power k2, likewise. So this c is basically my k, k1, k2, k3, the count of what is the exponent of p1 in the prime factorization. So whatever is the exponent of p1 in the prime factorization, that is there in c. In answer, I'll add the combination of c. So the thing that I had pre-computed above. NCR n plus I minus 1 CI. So in this I can say this is n plus k1 minus 1 ck1. So combination of k, in that I have pre-computed this value. So this value I'll multiply to my answer. So this way I'll multiply this value for every prime. All these values would get multiplied to give me my final total number of ways, okay, which I'll return through the func. Okay, so this way I calculate the total number of ways, and once I have added all the number of ways, I'll print my answer. Okay, so I hope this logic is fine to you. From the code, if we try to analyze the time complexity, this is taking 16 to 60 time. This overall prime factorization is taking sqrt time. Okay, now this loop is running square root b times inside the loop. Okay, so this overall, this loop is running sqrt b times. Okay, and if this if condition is satisfied, now this if condition would be satisfied at max cube root of b times. So at max cube root of b times, this if condition would be satisfied, and inside the if condition we are calling the count function two times. Complexity for the count function is same as the func function. Complexity for the func function is iterating through all the primes. At max the number of primes would be log n, and doing the prime factorization overall would be log of b, you can say. This would be log of b, would be the total time it would take overall. So this overall func is taking log b time. So this count function would also take 2 times log b, or which is same as log b time. Okay, so these two are taking log b time. Okay, so overall this would take cube root of b into log b time. Okay, so this overall thing is taking square root of b plus cube root of b into log b time. This is the time this overall function is taking, and I print the answer. So overall what I can say is square root b 16 to 60 and square root b plus this thing. So overall I can say my time complexity is order of sqrt b plus cube root of b into log b. So this is the overall time complexity. Overall it would be something like 1e7 1e8 only, so this is fine. And my space complexity would be like, we are using this vector of size 60, all these variables, constant variables, this set would be size log b. So overall I can say like log b is my space complexity. Okay, 60 is also log b only. So this is my overall time and space complexity. Okay, so I hope this problem is clear to you. Okay, so I guess we can move to the next problem now. So the next problem is problem C. So frequently Robert is given an array of feathers with initial heights h1 to hm, which he needs to flatten, that is massage, until all feather heights in that array become 0. To do that, he can perform the following operation for cost 1 as many times as necessary. So pick an integer I and any positive integer x, and both change hi to hi zor x, hi plus 1 to hi plus 1 zor x. So just pick any index I, and for both hi and hi plus 1, zor them with the positive integer x that you picked. So zor any two consecutive values with a positive integer x. This is the operation you do. If it's not possible to make all heights 0 by applying the operation any number of times, then the cost is the length of array. So if you can make the overall array 0 by applying these operations, then it would be the number of operations required, would be basically your cost. For every operation, cost is 1. And if it is impossible to do it, then whatever is the length of the array, that would be the cost. Okay, now given an array A, determine the sum of cost to flatten all contiguous subarrays of A. So formally fh is defined to be the minimum number of operations needed to flatten h. Please calculate f of A L to R for every L less than equal to. So basically for every subarray of array A, you need to calculate the cost and add up the cost for every subarray. That is what you need to print in your final answer. Okay. So constraints are given as n is given as 1 is 6. You have to do something in order of n time. So keeping this in mind, let's look at one of the test case and understand what we need to do in the problem. Okay, so let's say you are given this array. So for this given array, you need to compute like for every subarray. Let's say you are taking this subarray. Then for this subarray, you would compute that if you can make this overall subarray equal to 0 with the operations, the number of operations would be your cost. Otherwise, length of the array is your cost. So here, let's see, we can we make it overall 0. So for this, the operation available to you is pick any two consecutive values, XOR it with x. Pick a x of your choice. So what you can do here? Maybe if you XOR both the values with, you want to make all of them 0. So this is already 0. If you XOR it with any non-zero value, it would become non-zero. So you would basically prefer not XORing it. Same way for this two consecutive elements, this is already 0. If you XOR it with any values, it would become non-zero. So you would prefer not XORing. So basically here, this 2 cannot be made 0. If you make this 2 0 with a XOR of 2, then this would become 0, but this would have become 2. So basically here you can say it is not possible to make all of them 0. So for this, the cost would be 3. The length of the array would be your cost. Okay, let's take some other subarray. Let's say we are taking, um, what subarray can we take? Let's say we are taking this subarray. Still it won't be 0. Let's say we are taking this complete subarray. Okay, I guess it would be 0. Yeah. So if you are taking this subarray, what we can do is for these two numbers, now since this is already 0, we'll not apply an operation here, because if we apply an operation, if you XOR it with x, this would become some x, which again we cannot reduce it back to 0. So you would not apply an operation here. Okay. For this again, you can apply, and now you want to make this 0. So let's say you XOR it with 1. So after XORing it with 1, this becomes 0, this becomes 1. Okay. Now let's say you look at these two values. This is 1, this is 0, this is 2. So let's say you pick x is equal to 1, XOR both of them with 1. So this 1 would become 0, 2 XOR 1 would make it 3. Okay. Now again, for these two, you want to make this 3 as 0. So what you would do is you would XOR both these two with 3. So after XORing, this value would become 0, this value would become 3. Now for this again, you would XOR with 3, both the values become 0. So after applying the XOR operation once, twice, thrice, and 4 times, and yeah, after applying the operation 4 times, in this particular subarray, in 4 operations, you are able to make all the elements 0. So cost for this subarray would be 4. If it was not possible, its cost would have been 1, 2, 3, 4, 5, 6. Size was 6. But since it was possible, the cost is just 4. Okay. So this way you need to compute the cost for every subarray present in the array. And if you compute the cost for every subarray, the sum of them would be your final answer. So here there would be a lot of subarrays. So its sum would be something like 72. If you look at some smaller arrays, let's say if you look at this array, then for this, the subarrays would be either take this would be a subarray, take this would be a subarray, take both, this would be subarray. These are the only subarrays possible. For this particular subarray, it is already 0, 0 number of operations required, already 0, 0 operations required, already 0, 0 operations required. Sum of them is 0. So final answer was 0. If you take this test case, then for this, one of the subarray is, so there are like, you can take this subarray here, here, here 3 times. So this would be present 3 times, and this 1 1 would be present once here. And if you take If you again take this subarray, then here also. So here two times this subarray is present, and one time this complete subarray is present. So this 1 1 1 is present one times. So for this subarray, the cost is, you have a 1, you cannot XOR it because there is only one element. At least two elements should exist in order to XOR. So you can never make it 1. Cost would be the length of the array, which is 1. For this, you have two ones. What you can do is select both of them, XOR it with a 1. You would make both of them equal to 0. So this way, in one operation, you can do it. So for this also, the cost would be 1. For this, if you XOR these two values, they would become 0 0. But again, if you XOR them, one of them would become non-zero. So you cannot make all the three of them 0 here. So its cost would be the length of the array, which is 3. So final cost is this 1 multiplied by 3, because there are 3 subarrays of this type. There are 2 subarrays of this type and 1 subarray of this type. Overall, it is 3 plus 2, 5 and 3, 8. 8 is your final answer. I hope you can get. Okay, so you would have got what you need to do. Now, how do you do it optimally? So like you can move to every subarray and then find it, but that would, going to every subarray would only take order of n square time. There are n square different subarrays, and then computing that answer would also take some time, but you have to find the answer in order of n time only. Okay, so before moving to the optimization, let's like try to find for a given array only. So let's say if for one subarray only, if you want to compute the cost, how do you compute that? What is the cost of a subarray? Let's try to analyze this thing. So if you look at an array, let's say you have an array A1, A2, A3, A4, A5. Let's say the array is of size 5 till A5. So first of all, what are the operations available to you? Select any two consecutive values, XOR them with some x. Select any two consecutive values, XOR them with some x. Two consecutive values, XOR them with x. Would you use the operation two times on the same values? Never, because there is no benefit of using the operation two times on the same value. If you XOR them with x once and then again XOR them with some y, better XOR with x XOR y one time only instead of XORing it separately with x and y. So whatever you are XORing, doing it one time or not doing it is the only thing available to you. So and what you can say, not XORing them, you can say it is like XORing with 0. Okay, so if you are not applying an operation here, you can say that you are applying an operation with x equal to 0. It's equivalent. So keeping that in mind, now you are telling that you are applying an operation every adjacent pair. So every adjacent pair, you are applying an operation. Let's say you are applying an operation that the first pair is XORed with x1, second with x2, x3, x4. Okay, this is the operation. So this array of x just represent the O. If you have fixed this array of x, fix these 4 values, then your final value of your array is also fixed after doing the XOR. What is the final value of the array? This A1 would be A1 XOR x1. Now what you need to make sure is this thing should be 0. Okay, so if this thing has to be 0, that means x1 and a1 should be equal, then only the XOR would be 0. That means what we can conclude is this x1 is equal to a1 only. This x1 is equal to a1. This is my first conclusion. Now, if I look at this second thing, then what value would I get at a2? It would be XORed with both x1 as well as x2. So here we would have, in A2 we would have A2 XOR x1 XOR x2. Now from the previous equation you can say that x1 is same as A1. So you can write it as A2 XOR A1 XOR x2, and this thing should be 0 in order to satisfy my final condition. So that means A1 XOR A2 XOR x2 is 0. That means what is x2? X2 is A1 XOR A2. So this way you can say that definitely your x2 should be a1 XOR a2. Okay, let's move to this a3. If you move to this a3, the condition we get here is x2 XOR a3 XOR x3 This overall thing should be 0. And what is x2? X2 is basically a1 or a2. So this thing is a1 or a2 or a3. So x3 should be the XOR of a1, a2, a3. That means x3 should be a1 XOR a2 XOR a3. This way you can say x4 is a1 XOR a2 XOR a3 XOR a4. So in this way and so on, what we can say that the intermediate values that you are getting, the value of the x which you would use for the XOR is basically the prefix XORs. The first value you would use would be a1, next would be a1 XOR a2, next a2 XOR a3, and so on. And what final condition it should satisfy? The final condition would be derived from a5. What is a5? A5, so this would become a5 XOR x4, and this should be 0. That means a5, so what is a5 XOR x4? So x4 was this thing, so you can say this was a5 XOR this whole XOR. So basically this whole thing is a1 XOR a2 XOR a5. Okay, prefix XOR till a5, this should be 0. If this prefix XOR till a5 is 0, then only you can say the last value would become 0 and our condition would be satisfied. And if this prefix XOR till a5 is not equal to 0, that means we cannot do it. We can never make all the values equal to 0, because from this, like we have proved that this x1 should be equal to a1 in order to make this 0. This x2 should be this in order to make this 0. This should be this in order to make this 0, and so on. This should be this in order to make this 0, and this overall thing should be 0 in order to make this 0. So if this overall thing is not 0, then we cannot do it. And if this is 0, then we can always do it. Take x1 as a1, this. Okay. And what is the, so what you can say is, what is the cost? So you can say that the cost for any array A is if the prefix XOR till n, okay, with prn I am representing the prefix XOR till n. If the prefix XOR till n is 0, then we can apply the operation. So my cost would be the number of operations applied. What is the number of operations applied? So you would not apply all these n minus 1 operations. Among them, all those values which are 0, if this XOR value is 0, then applying this operation using x equal to 0 is same as not applying the operation. So among these prefix XORs, the number of non-zero prefix XORs is the number of operations applied. So you can say that the number of operations applied is, you can say n minus 1 would be the total number of operations applied minus the count of zeros in the prefix XORs. So minus the C0, where C0 is count of 0 in prefix XOR of the array. So this would be the cost when the prefix XOR of n, the overall prefix XOR of the array, overall XOR of the array is 0. Otherwise, else we can say my answer is simply n. N is the cost of the array. Okay. So this is fine. So once you know the overall, once you know an array, after computing the prefix XOR of this array, you can get the cost for that array. Now we need to compute the cost for every subarray. So how do you do that optimally? So let's say you have this array A. So you would have this array A. Now you can, let's say, compute the prefix XOR of this array. You have computed the prefix XOR of this array. Now you have to compute the answer for every subarray. So you can fix your L and R one by one and compute for every array. Let's say you fix your L here. Okay, you start with all the subarrays starting from here. So one subarray would be this, one subarray would be this. So once you have fixed your L, you will move your r from here, 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 here. You will move your r forward. Okay. Now, let's say you have your r has reached somewhere here. Okay. So for this L to R, if you know the prefix XOR array, if you know the prefix array starting from L, so if you, while moving your R, you can keep computing your prefix array. So once you have computed your prefix array, you know the contribution of this to the total cost of this array to the total cost. What is the cost of this array? If the prefix XOR at this position R, okay, so let's say this is the R position. If at position R you have a prefix XOR of 0, if it is not equal to 0, then you do a plus R, basically plus R minus L plus 1, whatever is the length, that much you will do. If it is non-zero, since R is fixed to 0, I am telling that you will do a plus R, full R. But if it is equal to 0, then what would you add? So if you, in the prefix array you have a 0 here, then it, your answer is n minus 1 minus C0, the count of zeros in this prefix array. So till here, how many zeros did you have? So, or you can say that n minus 1 minus C0 or n minus C0 plus 1. So the count of zeros till here plus 1. So, or you can say this is basically, this thing is basically the count of zeros till prefix R. So if there are 3 zeros, you would do say your answer is n minus 3. Okay, so like there are 2 zeros to the left of this 0, then in total there are 3 zeros, your answer is n minus 3. So the value that would be n minus 3. So if you look at the structure of this prefix array, then you can calculate the total sum for the fixed L for every R. If you calculate the total sum, let's say you have in the prefix array you have zeros at these points. So for all the R from in non-zero points, you would add plus R to the answer. For all the R's at points zeros, from R you would subtract some. Okay, this would be N, this would be R here, R here. Okay, from R you would subtract the count of zeros that have occurred till here. So here you would do minus 1, here you would do minus 2, here you would do minus 3, here you would do minus 4. So what is the total subtraction you did? Total addition you did, consider all of them as RRR. So for this you would add plus 1 plus 2 plus 3 plus 4. So 1 plus 2 plus 3 plus up till n. This much you added, and what you subtracted, if the number of zeros were 4, then you did minus 1, minus 2, minus 3, minus 4. So if I am telling that in the prefix array, if the count of zeros in the prefix array is C0, then I would subtract C0 into C0 plus 1 by 2, and this thing would be basically n into n plus 1 by 2 minus C0 into C0 plus 1 by 2. So this thing we can say is the, for a fixed L, just by looking at the prefix array starting from this L, if you know the number of zeros that have come in this prefix array starting from this L, then you can compute the contribution of all the subarrays starting from L as this. Okay. Now, what happens when you move this L forward? How do you update your answer when you move this L forward? You have computed your initial prefix array in order of n. Now, when you move this L forward, you need to update. If you can keep on updating your answer in order of 1, then only you can just move this L till n and find your final answer. So how can you update your answer? So when your L moves here, now your prefix array should start from here. So in this prefix array, for every element, this element, you have to just remove the contribution of this element from all these elements. Then you would get the prefix array with starting from this particular point. So how do you remove the contribution of this element? So what I'm telling is, what you need is, after removing the contribution, how many elements become zero now? So removing the contribution is again XORing with this value only. So after XORing with this value, how many values become zero? Would be those values which were previously. So if I'm telling that this value is x, so all those values which were x in this prefix array, they would now become zero after XORing with x. So you don't update this prefix array. Rather, what you do is calculate the count of x in this prefix array. So if you just maintain the frequency of every element in this prefix array initially when you computed a prefix array, then you can just, using that map of frequency, you can just get this frequency of x from here. Whatever is the frequency of x here would be the your new C0 for the next L. Okay, now when you move your L forward again, then basically in this prefix array, you need to XOR with this value. So now your X would be this whole thing. So in this particular part, so you would have to find that in this part, how many values have, how many values are equal to X, where X is the prefix or till here. So for every L, what we can say is, in this array A, when you are moving to every L, then you just need to find that if you had computed your initial prefix array, then in your initial prefix array, among all the elements from L to N, how many elements have a frequency, or how, what is the frequency of, what is the frequency of prefix L minus 1? Prefix L minus 1 would be the value with which, if you XOR all these values, would create the prefix array starting from this L. Okay, so if you XOR the prefix XOR of this to all the elements in this array, you get the prefix array starting from this L. So whatever, so the number of zeros in that particular converted prefix array would be same as number of frequency of prefix L minus 1, frequency of this value, okay, or this particular prefix L minus 1 is this value, which is the XOR of this value is this frequency of this prefix L minus 1 in this. So what you can do is, in the initial prefix array, create the frequency map for the initial prefix array, and then whenever you are moving to the next L, remove this element from the frequency map. Just remove the contribution of this element from the frequency map. So always in the frequency map you would only have these elements, and in that frequency map you can get the frequency of this element to be your C0 for that particular L. And once you know the C0 for that particular L, you can add to the answer this thing. Now this N would become, actually I should write that as N dash, where N dash is the remaining length, which is N minus L, you can say N minus L plus 1. If L is 1 based, it would be N minus. So from N to L, what is the remaining length? Okay. So this you can say is what you would add to your answer while moving your L forward. So this way, in order of N time, you can compute the overall answer. Okay, I hope if this logic is clear to you. Let's do a quick dry run on let's do a quick dry run on this test case only. So what I'm doing here is, first I'll compute the prefix XOR of this whole array A. So prefix XOR is, for 0 it would be 0, 0 XOR 1 would be 1, 1 XOR 0, 1, XOR 2 would make it 3, 3, 0, 0. So this is the prefix XOR array. Now I'll start from this L. With this L, what is the frequency of zeros? Frequency of zeros in this prefix array is 3. So I have maintained my frequency map. Okay, frequency map, in that I say the frequency of zeros is 3, frequency of ones is 2, frequency of threes is 2. Okay, so this is the frequency map which I have maintained. Now in this from this frequency map, for this L, For L equal to 0, I'll say whatever is the count of zeros, that I'll say as C0. So in my answer, I'll add answer plus equal to, here n is 7. So 7 into 8 by 2 minus count of zeros is 3. So 3 into 4 by 2. This I'll add to my answer. So this would be 7 into 4, 28 minus 6, 22, I guess, if I'm right. Yes, this would be 72. Okay, then I move my L forward here. When I move my L forward, okay, then I'll remove the contribution of this element from the frequency map. So I'll update my frequency map by removing the contribution of this element and make it frequency of 0 as 2. Okay, so this contribution got removed. Now for this particular L, I'll check in my frequency map the frequency of prefix L minus 1, that is this. I'll check the frequency of this. So I'm checking the frequency of 0 only, which is 2. So now my C0 is 2. So in my answer, I'll do answer plus equal to. Now the remaining length of this array is 6 only. So it's 6 into 7 by 2 minus this frequency is 2. So I'll do 2 into 3 by 2. This would give me 21 minus 3, 18. Okay. Okay. Then I'll move my L forward. So before moving my L forward, I remove the contribution of this thing from my frequency map. So frequency of 1 gets removed. So frequency of 1 becomes from 2 to 1. Okay. Frequency map is updated. Next, for this particular L, I've moved my L forward. I'll check the frequency of prefix L minus 1. So frequency of prefix L minus 1 is 1. So this frequencies or 1 is the frequency I'm checking. So frequency of 1 is 1. So I'll use that 1 as my C0. So the new length is 5 into 6 by 2 minus 1 is my C0. 1 into 2 by 2. This would give me 15 minus 1, 14. Okay. Next, I'll remove the contribution of this thing. Make the frequency of 1 as 0. Move my L forward. Likewise, I'll continue moving my L forward till here and add up all these and to my answer. To get my final answer, I'll get as 72. Okay, so I hope it is clear to you the algorithm. Let's look at the code. So what I'm doing here is I take the input. Sorry. So I take the input. I create the frequency map. Okay, so I'll do the prefix XOR. Okay, so while doing the prefix XOR, so in XR equal to 0, XR XOR equal to AI. So I compute the prefix XOR in XI. I do frequency of XR plus plus. So I've computed my frequency map for the prefix array. Okay, now so for this prefix array, like I'm not creating an array, rather I only need the frequencies. So in a variable only I'm computing the prefix XORs and updating my frequencies. You can create this prefix array also, no issues. Okay, so I'm just using a variable only and updating my frequency map because I only care about the frequency map. So I've created the frequency map. Then for the initial L equal to 0, my answer is f of n minus f of frequency 0. So where f is just n into n plus 1 by 2. So f of n is just n into n plus 1 by 2. So here I do f of 7 minus f of 3. Okay, so here I'll do f of n minus f of frequency of 0. This would be my initial answer. Then I'll start iterating from I equal to 0 to n. So I'll move my L forward. So moving my L forward basically means, so if I'm at I equal to 0, then my L is basically I plus 1. Okay, so I'm removing the contribution of this I. So first I'll remove the contribution of this I. So XOR in XR I start with 0. So again I'm computing the prefix XOR. So I have to remove the prefix XOR of L minus 1. So since L is I plus 1, prefix XOR of L minus 1 is prefix I. So current prefix XOR. So frequency of XR minus minus. So in this way I remove the frequency of the current XOR. And then in my answer I'll add f of n minus I minus 1. So if I have moved till I, that means I have removed the first I elements. So n minus I minus 1 in 0 based indexing. So I have moved till I, then I have removed total I plus 1 elements from the array. So after removing I plus 1 elements, n minus I minus 1 is the elements remaining. F of that is the n thing that we would add minus f of frequency of XOR. So frequency, whatever is the current prefix XOR, frequency of that would get added to my answer. Frequency of XR gets added to my answer. So this way I am updating my answer and calculating for every fixed L. Finally, I print my answer. So if you look at the time complexity, this input part is taking order of n time. This updating a map would take a log n time. So overall, this is taking n into log n time. Okay. And this is order of 1. This loop is running n times and all are order of 1 operations. So this is taking n time. So overall, or updating my frequency would take log n time. So this would also be overall n log n. So overall, I can say my time complexity is order of n into log n. Okay. And my space complexity would be order of, we are just using a vector of size n. Frequency map would also be of size n. So order of n only. Okay. So I hope this logic and code is clear to you. Okay. So let's move on to our final problem, which is problem D. Okay, this is an interesting problem. So what you are given here is Alice and Bob are back to their favorite restaurant named Dumzo. Okay, whatever. They are sitting on opposite sides of a long table with Alice on the left. Between them are n plates expressed as a string from 1 to n, each containing either almond jelly or BBQ bao. Okay, so basically you are given a string of size n. Every character in the string is either A or B. Okay. Now Alice only needs almond jelly, Bob only needs BBQ bows. So they take turns eating as follows. Alice will select an almond jelly plate of her choice and pull a very long table until the plate is. So basically, if Alice would pick an A and all the elements before that A would be removed from the string, you can say. They would be pulled on, the dishes would crash. Okay. Same way, if Bob would pick any particular B and all the elements in the suffix of B would get removed. So this way they would repeat the operations until every dish is either eaten or knocked to the ground. Now, if on a player's turn there is no remaining dishes of their preferred type, they will skip their turn without doing anything. So if all the A's are finished and it's Alice's turn, she has no operations to do, she would just skip her turn. Now, each player wants nothing more than the satisfaction of eating the last remaining dish on the table, and both choose which dish to eat based on that who will eat the final dish. So the aim of both of them is to eat the final dish. So if finally the dishes remaining are all A and Alice eats the last A, Alice wins. And if the final remaining dish is B and Bob eats that last B, then Bob wins. So both of them would try to play optimally in order to win, or basically eat the last dish. So you have to find out if both of them plays optimally, with Alice starting first, who would win the game or who would eat the final dish. Okay. Constraints on n is given as 6e5. So you can do something like order of n or n log n only. Okay. So keeping that in mind, let's try to solve the problem. So if you look at the test cases, so let's look at one test case. So here you are given this string. So basically Alice would start first. So on Alice's turn, what she would do is, if let's say Alice selects this particular dish, then she would remove all this from the string and only thing left out would be this. Then it would be Bob's turn. Let's say Bob only has one way, picks this, remove all of this, and only this much is left. Then Alice, maybe she picks this, remove all of them. Alice eats the last dish, so Alice wins. Or another way to play the game would be something like, let's say Alice picks this particular dish, this gets removed. Among this, let's say Bob picks this particular dish, this whole thing gets removed, only thing left is this. Then it's Alice's turn. She has no available dish, she would skip the turn. Then in Bob's turn, he would pick this, Bob eats the last dish, Bob wins in this case. Okay. Now, again, both of them would play optimally in order to win. So, for optimal play, in this particular case, what would be the most optimal play? What can Alice do in order to win? So, one way would be, let's say Alice picks this dish. Okay. Then all of these dishes would be removed. Only thing left would be this much. Now, when this much is left, after this, the only possibility for Bob is only thing Bob can do is pick this dish and remove this. And then only A's are left, so Alice wins. So if Alice starts with this particular A, she is sure that she can win. So she would start with this particular A. So we can say in optimal play here, Alice wins. Okay, so answer for this test case was Alice. Let's say, let's look at this test case. Here, if you look at this test case, then it's Alice's turn. Only available option for Alice is pick this. If she picks this, this gets removed. Only thing left is a B. Then Bob picks that and Bob wins. So here only play possible was Alice picks A, Bob picks B, and Bob wins. So likewise, you can understand for, let's say, this test case, Alice can pick this one, remove the whole, all of the dishes. Alice eats the last dish, she wins. Okay. So now how do you find the most optimal play? Okay. So in order to understand like these type of game theory problems, one thing is always try to observe things from the base. Okay. This way you can find some pattern or something. Or when do you think is something like one person is confirmed to win? With what move one person can make assure that he is winning, and like the state that the game reaches is something which is which confirms the loss of the other person. That is a winning move. Okay, so if I'm telling that, let's say one base case you would have got from here only, that since Alice is starting first, so in the string, if the last element of the string is A, then Alice can always remove this A and just remove all everything and win. For this case, you would say that Alice always wins. One this base case you can like easily analyze. But up, so that means if string is ending with A, just print Alice. Now we only need to deal with all those strings which are ending with B. So all those strings which are ending with B. Now, what is the condition for Bob to win? Again, Bob can win if the first element of the string is a B, but it is the chance of Bob then only. Since Alice is starting first, so in the initial string, if the first element is B, maybe Alice can play a move in some A in the middle and remove that B from there. Then Bob won't win. But if after the move of Alice, if the first element of the string is B, then we can say that then Bob wins. So this we can say that this is a win condition for Alice if it's the turn of Alice, and we can say that this thing is a win condition for Bob if it is Bob's turn. Okay, so both of it then would try that you never reach, you never play a move so that the other person gets this win situation. So Alice would never play a move so that the first element left is a B. So whenever Alice plays a move in the string, if Alice plays a move here, then the string left would be a suffix of the string. So the element just next to it, if that is B, that means Alice would lose here if Alice plays that move. So Alice would never play a move. So if there is a B, Alice would never select this A. Same way, if there is a B, Bob would never select this B because after that, this prefix would be left ending at A and Alice can win. So one like base case would be obviously clear to you. If you are given something like AB, then the only possibility for Alice is remove this A, because there is no other choice for Alice. So she would have to remove this A. Then Bob can win. But if there are two A and a B, then Alice has a choice of removing this A. So Alice can remove this A, and then Bob gets this AB situation. So it's a AB is a losing state. You can say this is a losing state for any person. If Alice gets this, he would have to remove this and Bob wins. If Bob gets this, then Bob would have to remove this and Alice wins. So in this, what can Alice do is remove this and give a losing state to Bob. In this way, Alice can always win. Okay, so in this case, you can say that Alice wins. What if it is AABB? If it is AABB, then if Alice removes this, you get a BB, that means Alice loses. So Alice would never remove this. But so Alice would definitely remove this only. This is the only choice with Alice. So if Alice removes this for the remaining, again, for Bob, if he removes this, Alice gets a, that means Bob loses. So Bob would remove this only. So you get to this situation of AB, which is a losing state for Alice. That means in this case, Bob wins. So here, whenever you have some pattern of A's and then B's, for this particular type of string, what you can say, who wins? So always in this case, Alice would remove from here one by one, Bob would remove from the end one by one. So if there are more number of A's than B's, then Alice wins. And if number of A's are less than equal to B, even for equal case, you can say that equal case for that also is a losing state for Alice. That means Bob was winning for equal case. So for A less than equal to B, you can say Bob wins. Okay. This one base case you have analyzed. Okay. Once you have analyzed this, what we can say is, now you in your string you would have something like, there would be some sequence of A, some sequence of B, then some sequence of A, some sequence of B, and so on. So if finally you reach only one sequence of A followed by B, then you can determine your answer. But for any other random sequence, it is a bit tough to determine. So the next observation here is, when, like from this, when you reach the final state, in the final state, Alice would try to maximize. So after some point you would eventually reach to this state, and after that some person would win. This we can say. Here you may say that the number of B's is 0, so you reach all A's, Alice wins. Or you can say number of A's is 0, so you reach all B's and Bob wins. That can also happen. Basically, you would finally reach a state where there are CA number of A's and CB number of B's. And when you reach this final state, the solution is simple. Alice would try to reach a final state where there are more number of A's. Bob would try to reach a final state where there are more number of B's. So always both Alice and Bob would try to. So whenever Alice plays a move, she basically removes a prefix. Whenever Bob plays a move, he basically removes a suffix. So whenever Alice plays a move, she would try that after removing that, she would initially in the string there would be some count of A and count of B. Final aim for Alice is make the count of A to be more than B. For Bob is to make the count of B to be more than B. So Alice would always try to remove a prefix, so that in the prefix there are more number of B's than A's. So if she is removing more B's and less number of A's, then that is a profitable thing for Alice. And same way for Bob, he would try to remove so that there are more number of A's than B's. He would try to remove a suffix where there are more number of A's than B's, so that he is reducing the A's more, so that the count of
B is increasing relatively. That is the thing they would try to do. Now, while trying to do that, they would also try to make sure that, okay, I am trying to remove more number of Bs, but also if you can make other person reach a state where it is like impossible for the other person to remove more number of A's than B's. So if Alice can remove some prefix, so that for the remaining suffix that you have, for this remaining suffix, if let's say it becomes impossible for Bob to choose any such suffix where frequency of A is more than frequency of B, then basically Bob would be removing more number of B's always. So relatively after that, the number of B's would be, if they are less, they would remain less. So what I'm telling is, if Alice chooses such a if Alice chooses such a index I, so that for the remaining suffix, I'm telling that in the remaining suffix, okay, so what I'm telling that, let's say, okay, so let's say you have a string, so with some A's and B's, so Alice would choose such an index I, so that if you remove this prefix, then for the remaining suffix, first thing is, if in the remaining suffix the count of A's is more than or greater than equal to count of B's. Okay. So if the count of A's is greater than equal to count of B's, and also if C can make sure this condition is satisfied, along with that, whatever suffix of this Bob picks, whatever suffix Bob is picking, for any of those suffix, they never satisfy. Bob would try to pick where count of A is greater than count of B. So if this condition is not satisfied, basically for every suffix, all the counts are count of A are less than count of B, or even less than equal to, still it's fine. Then you can say that you have chosen such a I, so that for the remaining string, the total count for the remaining string, the count of A's is more, but for any suffix of that string, the count of A's is less. So that whatever suffix Bob chooses, Bob would reduce more A's only. So whatever suffix Bob chooses in the remaining string, this condition stays. The count of A's stays to be greater than count of B's, because Bob would be removing more B's than me. So always in this way, Alice can make sure that the count of A is more, and if Alice can always make sure the count of A is more, then Alice can finally win. Now, which is that optimal I? So how can you do this? That in the overall, in this suffix, the count of A is greater than equal to count of B, but in any other suffix, the count of A is less than equal to count of B. That means this I is the first point. That means you can say this I is the first point where this overall count of A becomes greater than count of B. So this would have an Alice only, since Alice is removed. So till here, I am trying to find a condition where count of A is greater than count of B. Okay, so if you include this ith index, then I can say count of A is strictly greater than count of B. So if from the right, if I is the rightmost point where count of A becomes greater than count of B, then for all the points before that, count of A is less than equal to count of B. So for any suffix before that, count of A is less than count of B, and I is the first point where count of A becomes strictly greater than count of B. Then pick that particular I. If you can get any such I, pick that I. If you pick that I and remove this whole thing, then for the remaining string, what you can say, that for the remaining string that is remaining, count of A is more or equal, even so it would definitely be equal, because this is the first point where the count becomes strictly greater. So till this point the count would be equal. This you can understand. So for this first point this count would be equal, and for with this a the count of a increases. Okay, now we know the count of a and b are equal, and for any suffix the count of a is less. So if you like try to like draw. Okay, so now for this string, for any suffix the count of a is less, b is more. Now whenever Bob applies an operation here, let's say Bob picks something like this, he would apply an operation here, he would remove this whole thing, and the thing we would be left with would be this much. Now for this leftover thing, at max what can Bob do? At max what Bob can do is CA, he can apply an operation when CA is equal to CB. So at max he would remove equal number of C and B, and still for this CA and CB would remain equal. But what I'm telling is it would not remain equal. If Bob, I'm telling that this is such a point where Bob applies an operation, and for this much point CA is equal to CB, okay, and Bob is applying an operation, then for this suffix you remove one CB, that means CA becomes greater than CB for this suffix. So if you are telling that in this suffix CA is equal to CB, that Bob can pick a suffix where CA is equal to CB, that means for this previous suffix CA was greater than CB. But you know in any of the suffix this is not satisfied. So this contradicts the thing. That means whatever index Bob can pick, for that CA would be strictly less than CB. That means whenever Bob applies an operation, he is reducing the count of B's. So after Bob applies an operation, for the remaining string, the count of A's would be more than count of B. Okay. Now in this string, you have count of A's more than count of B's. Again, from the rightmost part, from the right, you can pick the first index where count of A is strictly count of B. You would definitely get one such index, since for the overall string it is greater. So again apply the operation on that index, the situation repeats itself. So whenever it's Alice's turn, the count of A is more than count of B. So it would never happen that the count of A becomes 0 before count of B becoming 0. So you can say that Alice wins for sure. So what we can say, when the, if you can find any particular index I such that the suffix in the suffix of I, so if we can find any such I such that count of A is greater than count of B in suffix I, in the suffix array starting from I, if the count of A is greater than count of B, if we can find any one particular index I, that means just take the last that you found and Alice can win. So if I can find that, then I'll say definitely Alice wins. Then I can say definitely Alice wins. Okay. Now what about the case where we cannot find such an index? That means, okay, so for the otherwise case, let's try to analyze the otherwise case. What happens otherwise? So otherwise you have a string where if you take any suffix of the string, there the count of A is less than or equal to count of B. Count of A never becomes greater than count of B. So that means count of B is always greater. So whatever prefix Alice chooses, so this you can see is kind of the same condition that was there with Bob. Once Alice chose that thing, after that, what was Bob left with? Bob was left with an array where for every suffix, the count of A was less than equal to count of B. Then picking anything Picking any suffix would mean that Bob is reducing the count. Same thing would happen with Alice here. If Alice picks any particular I, and that should have an A, okay, that means the remaining suffix that I give to Bob, for that remaining suffix, always the for that remaining suffix, I can say always count of A is less than equal to count of B. And I can say that is equality condition also doesn't hold, because if this holds, if they both are equal, then with an addition of A, I can say that till here, count of A becomes greater than count of B. But we know this never happens. That means this equality also doesn't hold. So whenever we apply an operation on I, the remaining string that we get for that count of B would be strictly greater than count of A. And once Bob gets a string where he has count of B more than count of A, same argument as we said for A, he can perform operations in the same way and maintain the count of B to be more than count of A and win. That means we can say in the otherwise condition, Bob wins. I hope this is clear to you. The with proof why this works. So in the code, we just need to find, just go start from the right end, start from traverse from n to 0, keep computing the count of A and count of B in the suffix. If at any point the count of A reaches more than count of B, just print Alice as your answer. If for any suffix the count of A never reaches more than count of B, print Bob as your answer. That's it. So let's look at the code. So what we can do is we iterate from n minus 1 to 0. In CA, I calculate the count of B, in CB count of A. If SI is equal to A, CA plus plus, LCB plus plus, I update the count. If at any point count of A becomes more than count of B, I print Alice and return out. Job is done. If till here I never print Alice and return out, then I print Bob. That Bob wins the game. Okay, job is done. So I hope the logic, proof, and everything is clear for this problem. Time complexity would be, obviously, I am just running a loop of n, so order of n time for the loop. Taking string as input would also take order of n time. So time complexity here would be order of n, and space complexity here would be, again, the string would take size n, so order of n. Okay, I hope this problem is clear to you. You enjoyed the whole PCD, liked the solutions. So thank you so much for tuning in. Goodbye.